Okay, so today we're going to be talking about the Lattice-Boltzmann solver, specifically in the pedestrian wind comfort application. And the case we've got for you is a validation case. We're going to explain to you why we need validation cases and what the case is and how this actually helps us in pedestrian wind comfort. But firstly, we're going to go through a few introduction slides, just kind of explaining who SimScale is, what simulation can do for your workflow, and also just explain the case and where it came from as well. So, firstly, my name is Darren Lynch, and I'm experienced in CFD. I come from a background of CFD and engineering design. I studied aerospace engineering at Brunel University, and I've recently graduated, and I'm now part of the application engineering team here at SimScale. What we're going to do today, just benefits simulation, introduction to SimScale as I mentioned, today's topic, which I briefly covered, a live demonstration, so we're going to go onto the platform itself and show you how we set up this case on our platform, and more particularly going over the kind of things that are sensitive to getting valid results. So we'll step more into that when we come to it. And then we're going to go for a result summary. So we're going to show you the visualizations and the graphs in which we say that this case is valid and our solvers are valid because, and they are valid because why. And then we're going for a QA session. So you guys get to ask me things about this case, things about pedestrian wind comfort, SimScale in general, or just, hi, how you doing? So we're going to move on. So the benefits of simulation. So to really grasp the benefits of simulation, you've got to think about what would happen if we did not have simulation. Okay, so if we were to test a design or a scenario, how would we do that? So we'd probably design our case, we'd have it manufactured, we'd test it, we'd determine whether it was actually fit for purpose, and then we'd probably iterate a few times, and then at the end we'd have a design that we could probably go through and manufacture. In contrast, however, if we bring simulation into our workflow, we have to remember that we can get rid of a lot of those physical prototyping steps. That's going to reduce time. It's going to minimize costs because we're not having to manufacture, test it in, say, wind tunnels or other experimental equipment. We can actually run more scenarios at a time. So, for example, if we were designing a pump, how many different things can you change at once? Probably one iteration, one change at a time. With simulation, you could do 10 different changes and see what impacts they had. And finally, what we're going to do is we're going to test the correctness and the efficiency of your final design. Now, some companies might not have been able to afford the physical prototyping and might have got to the end of their design process and found that it actually doesn't fit purpose. So these are huge advantages of simulation. But more specifically, today we're looking at the architectural engineering and construction side of things. So we're looking at buildings, thermal comfort and things like that. So how does simulation really help with this specific application? So what we're able to do with simulation is we're able to, for example, predict wind loads on buildings, or we can predict pedestrian comfort, air quality, contamination. We can also optimize thermal comfort. So inside the building, what is the temperature, what velocity from the HVAC systems is affecting the people. So these are all huge advantages of simulation. And today we're just going to look at one of those very small areas, but it's good to bear in mind that SimScale can cater for all of these different scenarios. So an introduction to SimScale then. So SimScale, obviously we've covered, we do engineering simulation, but we're more than that. We're a cloud-based simulation platform that does everything in your browser. So just to grasp what that actually means, we're going to go to the next slide. So we can do everything in one. So we have a platform that is capable of doing fluid analysis, structural analysis, thermodynamics through the forms of CFD, FEA, etc. We've got real-time support, so we pride ourselves in real-time support. You can pick up the phone and chat to us. We answer emails. We have a little dialogue box that allows you to chat to us. And also we provide consultancy, webinars such as this, and training. But the real advantage, I suppose, comes from collaboration. So if you are having a problem, you can chat on the forum. As I mentioned, contact us. Or, because it's all in the cloud, you can just tick a box and we'll be able to look at your project and get you unstuck. Additionally, if you start a project from completely from scratch, you can pick a public project in which to start your investigation from. So you can pick an example project and start from there, and that gives you, a lot of advantages in terms of where do I start, what have I got set up, how do I get valid results in this case. You could do that just by picking one of our many simulations from the public projects available. It's fast and easy. All you have to do is upload a geometry and start working on our cloud platform. You don't have to have huge amounts of local processing power because it's done on our servers, and you can run as many simulations as you want in parallel. So traditionally, if you have a local hardware, you run one simulation at a time, and that's how you get the most efficient solves. However, with our platform, you have many instances where you could just fire simulations too, and you get just as much processing power on each of those simulations that you're firing off. And that is a huge advantage for a cloud-based platform. And finally, we're very secure. So we use government-approved encryption systems, where a majority of the time we're actually going to be more secure than your local hardware. So it is a huge advantage using a cloud-based simulation software such as SimScale. Okay, so we're going to discuss today's topic. We've recently brought out a Lattice-Boltzmann solver. That is an extremely fast, very efficient transient solver for incompressible flows. And it's useful for many applications, one of which is pedestrian comfort, and that's what we're going to be looking at today. So what we want to do is we want to say, okay, we're running a simulation. How do we know that the results we're getting are accurate? Well, the answer is we need to run a validation case, because not only do we need to have trust in the solver, but we also need to understand from an engineering perspective what leads us to valid results. In the next few slides, I'm going to outline what this case does and where it comes from. And later on, we're going to kind of discuss the results, the meanings, and how accurate it actually is. So the AIJ is the Architectural Institute of Japan. They put together a series of about 6 or 7 validation cases in which CFD companies or CFD users can use as a validation case for pedestrian wind comfort specifically. So what that means is if we were looking at flow through cities or smaller areas, then we can actually use these validation cases to make sure that the results we're getting is accurate. Most of these cases take measurements at pedestrian level, so that's about just under 2 meters in height. Of these 6 or 7 cases, we're using the second before last in terms of complexity. So case E is actually one of the highest in complexity we can go for the validation cases. And it's actually based on a city called Nagata in Japan. And this is how the geometry looks from a simulation perspective. So we've got some buildings of interest, which are the large ones on the left and the 2 small ones on the right. And that's highlighted in the top left in a dark colour. So this is the top-down view, and you can also see numbers on the plot. And they are our probe points. They're what we're going to be measuring. So in the wind tunnel, they measured those points. We're going to be using those points to tally it up against our CFD results. So pedestrian wind comfort is a function of the mean velocity. So the AIJ recognised that, and all of their validation data is normalized velocities. So when we say normalized velocity, it's the velocity at a point normalized with velocity at another point. So we've done the same and compared the results. We can also, since the Lattice-Boltzmann solver is a transient solver, we can also explore the transient data, and that could give us a clue as to how turbulent a certain area, what gusts we would get due to the mean velocities in the profile. But we'll explain a bit more of that later on. So the background, the Lattice-Boltzmann solver that we've recently introduced, it uses collision theories to predict the fluid behaviour. Some advantages are that it's less computationally expensive. It is highly parallel, so we're able to use our GPUs to accelerate this. And it's also simple and very easy procedure to actually create. And one of the biggest advantages is it doesn't matter how, it can perform better with more robust, perform better with worse geometries basically. So it's more robust. So the objectives of this simulation is to simulate wind through Nagata City after a proposed construction. So they're the results that we're comparing to. Compare CFD results to those obtained in the atmospheric boundary layer wind tunnel to assess the accuracy of CFD. Understand the sensitive settings to obtain accurate results, and analyze the probe signals for further significant findings. So it's important to use the atmospheric boundary layer in our simulations, and I'm actually going to show you how we upload an atmospheric boundary layer to the platform later on. However, for now, know that these atmospheric boundary layer profiles came from the paper itself, and we've input both velocity and turbulent intensity as a function of height at the inlet for all the directions. So I'm just going to briefly pause the this presentation, and we're going to go onto the platform, and maybe if you've got the platform open you can follow along yourselves, otherwise just follow along with me. We'll go through the more sensitive settings of the Lattice-Boltzmann solver setup in which got us these accurate results, and hopefully we can also see some results live as well. So this is our platform. Usually we start most simulations by uploading a geometry. In this case we've got an STL that's converted from the geometry made available by the Architectural Institute of Japan, and we've created a simulation which allows us to use the Lattice-Boltzmann solver. So when we've created a simulation we're able to use the incompressible Lattice-Boltzmann solver. This is only available for our paid customers, but if you get in touch with our sales team we'll be more than happy to start discussions off. We select the geometry like so under the geometry section, and we've got many geometry primitives in which have been defined. So the Lattice-Boltzmann solver uses geometry primitives for many different things. We can specify which volumes we want to export in the solver, and we can also define what mesh refinements we want from geometry primitives. So in this case we've got the external flow domain, which shows you a square around the flow domain. We've got a velocity level region refinement to make sure that the mesh is very fine in that area. And we've got many other export and refinements going on here as well. And that's important in, when we come to setting up the mesh, because we need to make sure that the mesh is fine enough to capture valid results. And we're going to show you the settings in which we found to produce those best results as well. So in the model section we're actually providing a scaling factor which is similar to the scaling factor that is run at wind tunnel level. And in materials, we're using standard air properties at 1 ATM. The boundary conditions are the only other real thing that we need to worry about before we get onto meshing. And in the Lattice-Boltzmann solver, instead of selecting a face to define your boundary conditions, you simply assign it to one of the faces on your geometry primitive. So we've got the X-min for velocity inlet, X-max for pressure outlet. We've got a no-slip wall for the floor, obviously for reasons to make sure that the profile is maintained close to the floor. And then all other walls are slip walls to make sure that there's no interaction with those boundaries. And then, as I was saying earlier, we use the atmospheric boundary layer provided by the paper. So here in Velocity, we've actually uploaded a CSV, which you can see here. You can upload that using the Browse Files function. And this is for Velocity, and you can also see similarly we've done it for intensity as well. And this makes sure that the not only that the profile has got the right velocity curve, as we'd expect from an atmospheric boundary layer, but it's also got the right turbulent intensity, so the fluid is going to perform correctly when it actually reaches the city itself. Another thing that's quite different about the Lattice-Boltzmann solver over our other solvers is that we've got quite a lot of options for exporting data. You have to be very careful what data you want to export, because it's so fast and it's a transient solver. We could store hundreds of millions of gigabytes of data without realizing. So we need to think about, okay, what part of this fluid domain do we want to pick up, and how do we want to visualize and manipulate that data? And really what we wanted to do here is we wanted to export probe points, because that's what we're comparing it to. And that is absolutely fine, because on the SimScale solver we are able to upload a CSV of all the probe points nice and easily, directly exported from our paper. And this list of points will be put into the domain, and will be all of the values will be picked up for these points. So that is the X component, the Y component, the Z component of velocity, which we're mainly interested in. Additionally, we wanted to get some transient outputs, just some profile slices to make sure that the solver was doing as we expected whilst we were solving. And we also wanted to transiently save the pedestrian area so that we could do animations later. And those animations we will show you in a bit. As you can see, they're very thin slices to make sure that this is efficient on memory, so that we don't run out of memory before the simulation is finished. And then finally onto the mesh settings. So the mesh is actually very sensitive to getting accurate results. And what we found is that certainly at the floor level, we need a very high refinement. In this case, on the inner pedestrian level, we've applied a 0.25 meters refinement on that. But going up a level, so I think floor, there we are. So going up a level, we've applied a 0.5 meter refinement in the direction of the wind to make sure that that atmospheric boundary layer is maintained across the floor all the way to the city. And then we basically gradient up from there. So we've got level 1, which is slightly higher of 0.5 meters, level 2, which goes to 1 meter, slightly higher than that, and then finally level 3, which is bigger and higher, and it goes up to 3 meters. And this mesh we found to give us very accurate results, which we will show you later. But whilst we're running the simulation, what we can actually do is we can monitor our probe points, which I will bring up now. There is a lot of data here, so it might just take a few seconds. But we can monitor the probe points to make sure that we've not hit a steady state, but made sure the solver is actually running to a time steady state. So this is your plot, and what you'd actually do is you'd be able to download these results to compare to your validation, your reference data, by downloading the CSV. And finally, at the end of your simulation, you will get some results that look rather like this. So you can see that you've got a very accurate, very fine result set where the turbulence is clearly visible. Okay, so you've got your high velocity regions. These break down very quickly into turbulent flows, and you've also got quite a lot of fluctuation behind the buildings in the wake in the low velocity regions. And what we'd actually do is we download these results from here if we wanted to process the transient results further. However, actually this is pretty good for us on the online platform. So we are viewing this live on our platform. And I forgot to tell you actually just to make this a bit more impressive, how big the mesh actually is. So this is running on 98 million cells, and it completed in 567 minutes. So if anyone knows the kind of speeds that traditional steady state solvers solving, you will know that that's actually a very fast simulation. So I'm going to go right now back to my presentation, and I'm going to show you some of these results in the slides and in comparison to the experimental results. Okay, so to start with, just to kind of give you an idea of the order of things, we've done a direction comparison for each of the solved directions. So we've got north, east, south, west, and for each of those cases we're going to show you the comparison for the probe points to the experimental data, and then we're going to show you what we call a linear relation, and I'll explain that more when we get to it. So starting with the north direction, you can see from the animation which direction the flow is going, and from the direction arrow, and the maximum velocity in this visualization is actually 5 meters per second. And looking at the plot in comparison to the experimental data, what we're actually seeing is a very close resemblance of the CFD results to the experimental results. But to really get an idea of how exactly that relates in numbers, we can do our comparison, which is the linear relation. So using the linear relations, what we do is we plot the experimental versus the CFD results, and what we would actually expect is to see a perfect line from 0 to 1 if the results perfectly matched up, and the closer to linear that we get, basically the better our results. So here we've got a Pearson's coefficient of 0.7, so we can say that it very closely follows the correlation. And from the linear graph there, you can see also that the results very closely resemble that linear relation that we're after. And we see the same thing with the south direction. Once again, very close correlation, and same for the linear relation. This time 0.79 for the Spearman's coefficient, Pearson's coefficient. But more impressively is when we get to the western, the east and west directions. So what we actually see for the east and west directions is an incredibly close resemblance. Now I'm sure you won't disagree that even in the smaller between 75 and 79, these probe points, where there's only small fluctuations, we get a very good resemblance there in the CFD results. And again, a very good linear relation, a Pearson's coefficient of 0.86 this time, so very accurate. And then for the west, once again, very, very similar, with a Pearson's coefficient of 0.81. So we've established now that actually our LBM solver and this setup that we've used gives us results that is very close to what we'd expect if we put the same geometry into a wind tunnel. But what other advantages do we have over a wind tunnel then? So we're similarly accurate, but we can do more. You know, simulation has its advantages too. So we're going to just walk through kind of what we can get from the LBM solver, and additionally how the LBM solver is kind of placed next to steady state solvers. So the Lattice-Boltzmann solver being transient and being able to pull this much data, we can actually get a 3D or a 2D plot, depending on how much data you want to pull, of your flow going through your city. Now that's something that we wouldn't be able to do necessarily easily with a wind tunnel. And what we're seeing here is we're seeing very strong fluctuations around the building of interest. We're also seeing consistently high velocities coming around that corner, and we're also seeing a lot of low velocity fluctuations behind the buildings as well. And this helps us understand what effect our buildings are going to have on the pedestrian comfort. In the next slide, what we've done is we've taken all of our probe points. So we presented before a list of probe points. And what we did is we plotted that over time. And we've taken the average and compared it to the average results of the experimental results. But we've got more data than that. We've got the time-dependent signals for each point. So that allows us to analyze the transient data. So would that be peak or minimum velocities? Or could it be root mean square results, or even standard deviation? You know? So it allows us to get a lot of information about each individual point. And that's presented here. So we've processed these signals for each of the points. We've displayed the mean in black. We've explained we've visualized the maximum in red and the minimum in green. And what we've actually done is we've taken the standard deviation, and that's shown in the dark grey colour, and we've put a standard deviation each side, which is pretty cool. You wouldn't be able to do that with a steady state solver. But we've also done is we've plotted 3 deviations and 4 deviations, and what we can actually see is the maximum and the minimums tend to lie somewhere between 3 and 4 deviations, occasionally going between 1 and 3. And that's interesting because if we think of this as a normal distribution, we could start having an idea of the probabilities in which these high velocity fluctuations are going to occur. And we could use the maximum minimum, or we could use, say, a set probability on a normal distribution and kind of find a probability that this velocity would occur, for example. And then finally, what we're going to look at is what we're looking at is a comparison between OpenFOAM and our Lattice-Boltzmann solver. And I think the first thing you pick up is that OpenFOAM is not a bad solver. In fact, it's accurate in itself. However, we do get an increased amount of accuracy with the Lattice-Boltzmann solver, and that is visible when we look at the R2 values. So here we've got the linear relations again. We've got the R2 value of 0.739 in this scenario versus 0.717 for OpenFOAM. So we get an increased amount of accuracy for the SimScale Lattice-Boltzmann solver. It's also not too dissimilar from OpenFOAM. So where is the advantage? Well, there is an advantage in accuracy, but more incredibly, there is a huge advantage in speed. So although we've solved a mesh that's 98 million cells large in comparison to 30 million cells in OpenFOAM, we've actually got a solve time that is 7 times faster for a transient simulation. So that's quite incredible in itself. But the other things we can do is, instead of just getting the mean results, we can also get time-dependent results and point signals. and they are very useful, either if you're doing a signal analysis for the spectral frequencies, or if you just want to know it as before, these sort of signal maximum and minimums. So to summarize what we've covered today, we've looked at this validation case, and we've established that although the mesh size was much larger in Lattice-Boltzmann, it ran about 7 times faster than steady-state OpenFOAM. It was slightly more accurate, and that was in all directions, and the transient results are available. Now, there is a clause that I've stated here at the end. We don't have the transient data from the Architectural Institute of Japan, so we haven't validated our transient data for pedestrian wind comfort, but we could probably imply from the accuracy of the mean results that they're going to be pretty good. I think that concludes my part in talking and my part in demonstrating the solver. So I think now I'm going to hand over to you guys. So if you have any questions, please type them to me, and I will go through and try and answer them to my best ability. So I've got a question: how does LBM compare to wind tunnel testing? So the best way we can actually compare LBM to our wind tunnel testing is through these charts here. So what we've got here is the experimental in the darker shade, and we've got SimScale LBM in the lighter blue shade. And what we're looking for is the normalized velocity. And if the velocity of the SimScale results are close to that of the experiment, then we would say that the results are valid. But we can't do that for just one point. What we've got is a huge list of points from the Architectural Institute of Japan, and we've taken their results from their wind tunnel testing, and we've plotted those against all of the equivalent points in our CFD simulation. So we've plotted those, and what we can see is that actually a majority of those points very closely correspond to our CFD results. And if we look to the one-on-one relation, so that is, if the experimental result is this, what is the SimScale result? What we'd expect is that straight line. So we'd expect a gradient of 1. And what we get here is actually very close to 1, 0.79 in this case, where you can also see that the points plotted along that line are pretty tight to the trend line there. Why is the footprint of the case circular and not square? So the geometry we use is taken straight from the Architectural Institute of Japan, and they've obviously taken a region in which they've got the region of interest, and they've drawn a radius around, saying, okay, 100 meters or so radius is where we're interested, so that's the surrounding area that we're going to import. So it's nothing we've done in terms of cutting the geometry to make it better. In fact, we can support many different varieties of shapes, so whether that be entire city blocks, small snippets of city blocks, squares, it doesn't really matter to us. As long as we can fit a domain around it, it doesn't matter if it's circular, square, anything you like. So this geometry was downloaded from the AIJ website. It was converted into an SCL format, and that is what we're using to upload to the SimScale platform. So this here, although it's square, this is actually a zoomed in region of the geometry they've provided, and not exactly what we're showing in the bottom is exactly what they've uploaded. Got a question: how does the mesh work? So if I quickly nip out of the presentation and back into the solver. So at the moment what we do is we have the meshing as part of the simulation process. So what you do is you set up your case, you'd set up your mesh, and then you'd press solve, And because meshing is so fast in the Lattice-Boltzmann solver, it's done as an initial step and then moves on to simulating. So the reason why it's so fast is because it's actually more of a Cartesian type mesh idea, where the mesh that's inside the buildings is removed, and the mesh that is in the fluid domain is kept. And it's a very high order accurate scheme that is used to find out where the walls are, and that is how, on a fundamental level, the LBM meshing works. So what we've got here is your overall mesh settings. There we go. So the rest of the bounding box the rest of the fluid domain that isn't defined is a coarse mesh. However, what we've actually done is we've done a lot of manual refinements to make sure that we get the mesh fineness in the regions that we need for these valid results. And those refinements are done either as a surface refinement here onto those buildings, or it's done as a region refinement around the buildings. And once again, you see this this sort of box. That is the geometry primitive that we defined at the beginning. So we can keep going back to geometry primitives and defining more to make sure that we've got the refinement that we need. Okay, the question here, does it run on CPUs? Obviously the instance that we send it to has CPUs for some processing reasons, but the solving is actually done on GPUs, which is one of the reasons why this solver is incredibly fast. So depending on the mesh size, we send it to some instance with quite a few GPUs, and because GPUs have got so many cores in which it can solve on, and because the solver is so parallel or parallel optimized, the results are able to be solved very, very quickly. So that is the reason for the speed advantage here. Even though it's a transient simulation, the speed comes from the fact that it's highly parallel and it runs on GPUs. So is it faster than traditional methods is another question. Yes, we showed the speed back here. So if a traditional method was a steady state simulation, then we could say that it was about 70 times faster. If we run an equivalent mesh, even though that's not realistic, then it would be faster still. However, if a traditional method was to manufacture this, put it into a wind tunnel, have a look at how your buildings are affecting the pedestrian comfort, then this is going to take more than 70 hours. This could take weeks, months, and if that then needs a redesign, you've got to reiterate over that. So that kind of not only shows you the advantage of SimScale LBM over steady state, but the real advantage over LBM and wind tunnel testing for pedestrian wind comfort. Is LBM available for community account? No, unfortunately it's not. So at the moment it's only for our customers, and that is because we use a different type of billing system called GPU, and GPU hours are slightly different to CPU hours. They're not available to most customers, and because of the sizes of the instance, you can quickly burn all of your core hours at once. So if you're unfamiliar with the software, you kick off a mesh that's, say, 1 billion cells, then you will quickly expend all of your account core hours, and you'll be left with nothing. What we want the best experience for our customers and our users of Lattice-Boltzmann solver. So we give you a little bit of guidance and some rules of thumb and help you really get to grips with the solver so that you can get the most out of your core hours, your trial, etc. So if you're interested in giving LBM a trial, then please contact us and we'll try and help you out. And if anyone else has any questions, just tap them in the box and I'll try and answer them for you. So I've got a question: what is the maximum Reynolds number I can run on the model? So it's a bit of a tricky question, and unfortunately it's one of those questions that ends with "it depends." But I will tell you what it depends on. It depends on how big a mesh you want to run, and incidentally, how much you want to spend on your simulation. So the bigger the mesh, the longer it's going to take to solve, the smaller the time steps, and I'll tell you why actually. It's because the wall modelling. So basically what you want to do is we've got a set of turbulence models that we use. Some of them are the detached eddy models, some of them are large eddy models, and some of them are just unsteady RANs. So we've got varying complexity there, and all of them have different requirements on the first cell wall distance. Now, because this is Cartesian, you refine at the wall. The more you refine, the bigger the mesh, and the bigger the mesh, the longer it takes. So, for example, if we had a Reynolds number at 1e⁶, your wall refinement would have to be very, very fine. And if you got to the point where your mesh was 300 million cells large, it's going to start becoming quite costly for you. However, it could be a simple geometry. If it's a simple geometry and not an entire city, as this case shows, then that might become more doable. And also we could use the detached eddy model simulation to kind of reduce those wall requirements and help you solve a higher Reynolds number. However, what we do have is a Reynolds scaling factor here. So if we do find that we're running a simulation and it's the Reynolds number is just too high for us to solve on the mesh that we're currently using, what we can do is we can apply some Reynolds scaling. Now, we do know that by scaling a geometry down, then the results are going to differ somewhat. However, there's many reports out there that say that in architectural engineering, particularly in buildings, so that's pedestrian wind comfort, wind loading and things like that, then the Reynolds scaling doesn't have a huge effect because of the amount of sharp edges. So you can just reduce the Reynolds scaling factor and be able to run it. But I would say that for most cases, a Reynolds scale of about 1/6 would need to be scaled back down. So although it doesn't explicitly answer your question, unfortunately it ends in a depends. That kind of gives you the background as to why you might need to either scale your Reynolds number or reduce the complexity of your geometry. Another question, does LBM work with deformable boundaries for fluid structure interface applications? No. At the moment, LBM currently only works with fixed geometries. So that has no interaction with the structure and how it would deform. So yeah, that answers that question without going too much into detail. At the moment, no, just static geometries. Okay, then I'm going to call it there. Say thank you everybody very much for attending. If you do have any questions, then please reach out to us either through our messaging system, on the forums, or via email. If you're interested in using the Lattice-Boltzmann solver or trialing it, then please get in touch with our marketing team. And I wish you all a good day. Thank you very much.